All right, let's go ahead and look through some of the information necessary to complete Lab 11. So this one's over Coulomb's law and has to deal with the charges, electrical charges, and how they push and pull on each other depending on size, distance, and type of charge. So this link is available several places, even inside the quiz itself. We're going to use the macro scale version of it. So we have these two, I don't know, mannequins or robots, and they're pushing and pulling on these different charges. Okay, so first thing we need to do is we need to understand the formula for Coulomb's law. And it says that the force, sometimes it's C for Coulomb force. You can think, force on charged particles that also starts with the C, is K times Q1 times Q2 over R squared. So where Q1 and Q2 are the different charges or groups of charges, and then R is the separation distance between them. It's R because you can be anywhere around in a circle and have the same force. The R squared shows up as part of the calculus that makes this formula, but there we go. Now, even just looking at this and where the variables are and understanding that we can have different types of charges, we can actually pull a lot of information from this before we even really start putting numbers in. K is a constant that I will show you in just a minute, so that's just something that's always the same. But if we have like charges, ones that match, either both positive or both negative, it won't matter. Then what would happen is we would get a positive answer for force. So if Q1 and Q2 are both positive or both negative, then that would tell us that we'd have a positive force if the signs match. And that means they're going to push each other away, so they will repel. Okay, and then if the charges are different from each other, so if they don't match, then what happens is we'll have one positive and one negative. The order won't matter, and we would get a negative force from this. And so because we would have a negative force, then it's the opposite of pushing. So, think negative pushing. It's a little bit weird to think, but it's pulling. And so that would mean that these are going to attract each other. Apparently I can't spell or draw right now. So let me see if I can fix that. All right. Okay, then a couple of other things that we can pull from this. If we're trying to maximize or minimize this answer, then we can think about what the different variables will do. So like I said earlier, K is a constant, so that's not really going to play into the first part of this. But if I want a bigger force or a smaller force, then I can change my different variables. And think about what would happen if I held one constant or a pair of them constant and then change the other ones. So like if I'm going to move these charges around and I want to figure out what's going to reduce my forces. So if I look, I'm not going to change these. Let's set them both to 4 because why not? I think that's in the instructions anyway. And if I look at the forces between these now, we've got 197 from each of those. If I move them closer, then now I've got almost 400. And if I start moving them back the other way, then notice that it gets smaller. So if I wanted to make the smallest possible answers by just moving these around, the biggest distance is going to make the smallest answer. And if we think about why that happens, so K is a constant. If we leave the charges as constant, then basically assume everything else is 1 except for what you're looking at. Then if I'm looking at the separation distance, I have 1 over R squared. And if we think about this, if I make R a bigger number, then I would have a fraction with an even bigger bottom. I would be taking 1 and dividing by something even larger, and that would make it smaller. So if I had a smaller separation, so a smaller R, then that's going to give me a bigger answer, bigger force. And then if I had a larger R, then obviously that's going to do the opposite, and that's going to give me a smaller force. Okay, then similarly, if I wanted to look at the charges, so let me set them back at, some position, put this one at 4 and this one at, let's do 7 and 3. That way they're a little bit closer to being symmetrical. And if I'm going to mess with the charges now, if I make the charge bigger, so notice that one gets a little bit darker color, and it's meant to be a higher charge density, so difference in color there, then my force is going up. And so now I'm up to 200 and something. If I increase this one, now I'm up to 500 and something. And so notice that bigger charge is going to make a bigger answer. Then if I want to go smaller with it, then I can decrease this to, and obviously if I make 0, then there's nothing here. There's an extent to where that stops working and changes directions, because if I swap signs, then I can get back to that same force, but what's going to happen is now these are going to pull closer to each other. So I'd have the same force number, but the opposite directions. So I want to make sure that I have the smallest absolute values, the smallest just regular number part. And so notice that if I'm decreasing these, that eventually the smallest answer I can get from this arrangement is the smallest positive charges. Okay, so that should also make sense, because if I'm going to keep, obviously again, K is a constant. I haven't talked about that yet, but I promise soon. If I keep my separation, my R is the same, we'll just make up a number. We say it's 1, whatever. Then all I'm really looking at is whatever I'm going to get from Q1 times Q2. And so if Q1 and Q2 are bigger, so if I have bigger Q values, then I get a bigger F value. And then if I have smaller Q values, smaller charges, then I get smaller forces, so smaller values for F. All right, and then, for the last time, K is a constant, so that's not really going to change anything, but we can see how these are going to work. Now, it gets tricky if you start changing Q and R at the same time, because if one changes more than the other, then it can swing the answer. But for right now, if we're only changing one thing at a time, either distance or charge, then we can see how the overall force is going to change. Okay, so let us see if we can start working through some numbers. So according to the instructions, we want 4 microcoulombs. So that's a mu. So Greek letters kind of similar to M. Means micro, or 10 to the negative 6. Does it show me? No, scientific notation is only on the forces. But micro means 10 to the negative 6. Okay, and then move the charges to different positions, dragging them around. So I want to move these, see the smallest answer I can get. So if I bring these all the way out, I can also change the charges. Okay, so to make the charge smaller, notice that this is dropping even further. If I minimize the other charge, and eventually I can get down to my minimum possible force. So it looks like that's going to be 0.899 newtons. Let's see if we can calculate this and make it match by using pure math. So let me get rid of the stuff we don't need. Oops, I have a little bit extra to erase there. That's okay. It's out of sight for now. We'll just leave it. Okay, so K is a constant, and that particular constant is roughly 9 times 10 to the 9. So it's kind of nice that both of those are 9s. Then the units are ugly because they're meant to cancel a bunch of stuff, but we get newtons times meters squared over coulomb squared. So the meters squared cancel the meters that get squared on the bottom. Coulomb squared cancels the coulombs from the Q's, and eventually it leaves over newtons, which makes sense for force. So this is a constant. This is a number that will always be here. Or, it's slightly rounded. It's really 8.98755 something times 10 to the 9, but this is really close. So we will have a very slight difference from what the simulation says, but we'll get close enough on the number that we'll know what's intended to be correct. Okay, then each of my charges, in fact, are 1 microcoulomb. So 1 times 10 to the negative 6. That's what that weird symbol means. So microcoulomb means 10 to the negative 6 Coulomb. Okay, and then we had a pair of those, so you can either square this or just write it down twice. And then I want to divide by the separation distance squared. So from the ruler that's here, that's in centimeters. And so if I have 10 centimeters, then that means 10 times 10. Centi means 100th part of. So we don't do this normally, but that in scientific notation is 10 to the negative 2. You could also just decide to cancel, or rather to convert into meters first. So bump the decimal over a couple times, it's 0.10. You get the same thing either way. But that's in meters with that scientific notation, or if you've done the conversion, and then that's going to get squared. Occasionally, you'll see this rewritten slightly, where the r squared is bumped up, but when it changes parts in the fraction, it becomes a negative exponent. So there's a couple different ways that this can show up. All right, then running this through and checking the units, I already made some mention of it, but now we can confirm that the meters squared cancel the meters that get squared from the exponent, then the Coulomb squared from the pair of coulombs that are being multiplied here. And if we run all of this through the calculator and we were able to do it successfully, then we get 0.9 newtons. Which, you know, again, if we're thinking decimal places and trying to make it match, 0.9 is the same as 0.900, and we're thinking about 899 versus 900, looking at, you know, decimal places like that. And they're obviously very, very close. The difference in the simulation is just the difference in the true value for K. So like I said earlier, it's really 8.987, blah, 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 which is why it rounds that way. Okay, so it worked, it matched. We got the answer more or less from what was here. Okay, if we want to go the other direction now, so we found the smallest possible answer. If we want to find the biggest possible answer, then we want to do basically all the opposite things. So I want to move these as close together as I can get them. So, you know, we can't make them actually touch, but we can bring them really, really close. And then we also want to make sure that we use the largest charges we can get. So as I'm increasing one, notice that the force is getting bigger. So if I increase the other one, I can make the other force even bigger. And notice in the animation, these robots or mannequins or whatever now have to push really hard to keep these things next to each other because they want to repel and push apart. So I thought that was a nice touch in the simulation. So it looks like the maximum force from this is 4,585.485 newtons. Okay, so let's see if we can confirm that by calculating manually and see where this is going to go. So I'm going to get rid of all of this stuff, and then we're going to try it again. So new numbers now, so I'll use a slightly different color. K, we're still going to use the slightly rounded version of 9 times 10 to the 9. It's just easier with all the rest of the calculator work going on. We want to remember that the units, again, are kind of ugly, but they're going to pretty much all cancel out. So that's not going to be too bad for too long. All right, then our charge, we had a pair of these that were 10 microcoulombs. So 10 times 10 to the negative 6 coulombs. 2 of those, you can either square this or write it twice. And then either take the r and raise it to the negative second power and put it over here, or just throw it on the bottom. Depends on your calculator which one's going to be easier to do. Our separation distance, so if that's at 4, and these are going to be what, 2s? 0.2, 0.4, 0.6, 0.8. So yeah, so second mark, basically 1.4, seems like. And that's times 10 to the negative 2, or divide by 100 to convert first. It's up to you. And then that's going to erase the second power just because there's an exponent in the formula. Similar to before, meters cancel, coulombs eventually cancel. We get newtons left over, which is great. Running all of that through a calculator, then from this we get 4,591.837 compared to 4585. So, you know, something like 0.1% error. remember that's just the difference between our rounded value of k and the true value of k. So, it seems like it worked out well enough. Okay. So that one matched. That's good. Let's see what else we've got. So we want to set to 4 microcoulombs for each of these. We want to set them 4 centimeters apart. Can I put this at 0? I can. So I'll just leave that at 0 and I'll put this one at 4. Okay, and then we're going to determine the forces between these, and then we want to calculate manually and check. So we want to run through a few different variations on that. So 89.876, we want to run through and see what little changes we need to make. So we are changing the charges again, and we're changing the separation distance. So notice that most of this is going to stay the same. So in fact, I'm going to leave all the stuff that is the same, and then I'm just going to pick a new color for the things that we're changing for this time. So like here, we've decided these are going to be 4 microcoulombs and then 4 centimeters. And what's kind of nice about this, you notice this 4 on the bottom is going to get squared, and then there's 2 4s up there. A lot of this ends up just canceling. And because of the value that we pick for K, then in the end, we get that this is roughly 90 newtons. And if we double check, we see that, yeah, that is a number that's really close to 90 newtons. So that worked. Okay, then in the next one, we want to change one of the charges to 8 microcoulombs. So this is still 4, that one's 8, so now we've doubled this up. And so if we look, 179.751. And if we think about this, this should make sense. It should be easy to predict what's going to happen here. Because if I change one of these, so I'll pick a color I haven't used yet, but if I double just this one, then the only change I've done in one place that doesn't have an exponent is I've doubled my answer. And so that made this go from 90 newtons from the original, and if we run that all through a calculator, to 180 newtons. So we can see that it basically doubles, it calculates out, and it works. Then in the next question, we want to change both of the charges. So just as a reminder of what that value is, if these are both set to 4 and 4 again, we have this answer that's a little under 90. Now, if I'm going to double both of these, so I think you can predict if I'm doubling 2 things, then will have a greater effect on my answer. All right, so now both of these have been changed. So I have a ×2 and another ×2, and if I run this through a calculator, then it works out as well, and I get 360 newtons. So ×2 and ×2, same as ×4, 90 × 4 is 360, then it all seems to work out. And notice I'm only making very small changes to this formula. So yeah, 360 is really, really close to 359.5, and it works as expected. Then the last little group here, and this one can be potentially a little bit harder to follow in some of the math, just because it's on the bottom of a fraction and it has that exponent. But if we reset this back, and we don't know really what's going to happen yet until we start messing with this, but if we bring these back to be 4 microcoulombs each and the position of 4 centimeters apart, then I want to change my position this time and see what's going to happen. All right, so we're back to 90 newtons, which is, again, 89.876. That's the rough approximation. According to the question now, I want to cut the separation distance in half. So where these were separated by 4 centimeters, I want to bring this down to 2. And naively, you might think, okay, well, if the distance is a half, then I used 1/2, and the answer is going to be half as big. But you'll notice that this is actually a lot bigger than our original answer. And so let's explore that and let's see why. So if I change my separation distance, my number on the bottom, and instead of making it 4, I make it 2. Then notice that I'm dividing by something much smaller, which was mentioned in an earlier question. And then, if I run this through a calculator and I double check, then I'm going to get 360 newtons, which again probably doesn't do what you expect. But it's weird. The math checks out in the calculator, and in the formula, even if you're really careful, you can even see it happen. So what's changing here? The only thing is changing is the r squared that's from the bottom. So we change the r, it has an exponent. Both of those things are going to be important. So if I look at how they change for just this part of the fraction, then I'm taking my r and I am replacing it with half of r. And this is a manipulation that you don't see a lot of, but I'm going to show the process here because students had questions about it earlier in the semester. So I've got 1/2 of r that's going to get squared, and it's in parentheses, so that's something I want to pay careful attention to. So when I raise that to an exponent, then I can square each part. I can separate these, and because there's no addition or anything weird between them, then I can actually just square up each part. Okay, so the one on top hasn't changed. The r that gets squared is r squared. It kind of looks like what it said before. And then the 1/2 is going to get squared up and it's going to turn into 1/4. And if I look at how this compares to what I originally had, where I had 1 over r squared, then I can separate these out. And so I notice, okay, well, I have, and again, because there's no addition or anything, I am allowed to do this. But I've got 1 over 1/4 and 1 over r squared. And if I multiplied them, we could check it would turn back into this. The 1 over r squared is what we saw before. Then remember what 1 over 1/4 means. You flip and multiply, it becomes reciprocal, and we end up with 4 times 1 over r squared. So you don't necessarily have to follow the full algebra on that, but that's where this comes from and why it didn't necessarily work the way you expected. I suppose the shorter answer on that is fractions are weird, but it does work, right? 1/2 of the radius ends up being 4 times that part of the answer, and 90 times 4 is 360, which corresponds back to what we had there. So everything works. And that's it.